Alright, we ended our last video with this slide talking about how flow behaves in the upper levels, and I hinted that this was kind of the more, well, somewhat simplistic way of looking at things. So the issue is we live down on Earth's surface, and we have to account for friction when we try to do a force balance down at the surface. And friction, as we said, slows the wind down, and that's going to cause some other impacts to the resultant wind. And so here we go, surface wind balance. We got a lot of what we've already talked about, and now we throw friction into the fray. Friction slows the wind. But not only does it slow the wind, we know that the wind and the speed of the wind, let me say that a little bit differently. The stronger the wind, the stronger the Coriolis force. So if we decrease the speed of the wind, we're also going to have to decrease the Coriolis deflection. But we haven't changed the pressure gradient. And so that's why things end up crossing the isobars. I don't expect this to make sense off of a slide full of text, but it is one of those things that I would like to hope that you read over a few times and then think about in terms of how we discuss the individual forces. We still have the same pressure gradient at the surface that we would have aloft, but because friction slows the wind and the impact of the Coriolis deflection is related to the speed of the wind, the slower wind slows the Coriolis, and now we're going to end up deflecting the winds to the point that they cross the isobars in towards low pressure and out of high pressure. That in and of itself, the 30 degrees, good to know, but it's not critical. It's not where it has to be 30 and not 20 or 40. But the idea here is that the fact that they're going in towards low pressure and out from high pressure becomes really critical later on as we start to discuss the different types of weather associated with low and high pressure. The winds crossing in towards a low pressure means that the winds are coming together. They're converging. We heard this term and we talked about it a little bit back in global circulation when we talked about the intertropical convergence zone. Winds converging near the surface force rising motion, thunderstorms, clouds, interesting weather, to be perfectly fair, and the winds flowing out of high pressure are what are known as divergent winds. And that's going to mean that if you like quiet, calm weather, high pressure and divergent winds are likely what you're interested in. And so here's your surface wind balance. We basically keep our pressure gradient. We would have to have that, otherwise the wind's not blowing. We've already talked about the Coriolis, and now we add in the third term here, the frictional force. And so ultimately, as we had on the last slide, the Coriolis force has less of an impact. It turns less due to the slower wind. Coriolis is greater for a stronger wind, so depending on how much friction there is at the surface, we can really turn them pretty hard in towards a low pressure, or we can have a very small deflection in towards low pressure. That's why I said 30 degrees is a good average, but it does vary somewhat. It's not to where we're ever really going to get too focused on how rough is the surface, how much frictional force exists, but it is one of those things that when you're down near Earth's surface, it's going to be an impact. And so the Coriolis in and of itself does not balance the pressure gradient, and so we have to account for that friction, and that's going to make things a little weird. Perfect world, sun shining, no pandemic, we'd go outside and we'd try Bayes' balance law. The idea that if you stand with your wind at your back and you look like a real cool kid and put your arms out at your side and you can feel the wind and you turn clockwise about 30 degrees, your low pressure would be directly to your left. Believe it or not, we have done this in class, and it has turned out pretty well and accurate in terms of where the low pressure would be on a map. And so here is the balance in a schematic form. There is a portion of your lab this week that this will be invaluable towards getting done. Here's how I go about trying to draw the different forces that constitute the surface balance. First and foremost, always start with that pressure gradient force. Take the one to the bank that's always going to go from high to a low. At that point, you can think of this in a number of different ways. I just indicated that in the northern hemisphere, around a low, you're going to have a counterclockwise flow. And secondarily, winds are going to flow inward at about 30 degrees towards the center of low. So you have this counterclockwise flow around your low. and then it's turning inward. So in a weird way, it's sometimes as easy as to next just draw the surface wind. Here, inward and counterclockwise. Frictional force opposes the wind, 180 degrees, completely opposite, and then notice how the Coriolis is deflecting your wind to the right, and so it's at a 90-degree angle to your surface wind. There are a number of other ways that you can think about it, again remembering that the pressure gradient and Coriolis balance each other in other of our force balance equations, but here it's a little bit slower and therefore it's going to deflect in a certain way off to the side. Again, some of them are pretty simple. The pressure gradient's easy, and then once you get the wind, remember friction is simply going to oppose the wind. And so what we have up here in this upper right box, how the surface wind crosses the isobars in towards low pressure, is very critical. You have a graphic that looks like this on your lab with boxes on all four sides of the low. Some people, bonus hint, find it easiest simply to just rotate their paper and draw something very similar on all sides. Of utmost importance is to understand why the wind blows across the isobars. If we were to reverse things, turn it to the southern hemisphere, things get basically reversed in terms of how the spin goes. We're still going to have winds go in towards a low and out from a high in both hemispheres. Again, the winds will go in towards a low and outward from a high in both hemispheres. Because again, I keep talking about this like we're focusing on this low, we could be thinking of it from the perspective of this high, and therefore this wind is blowing outward across the isobars from the high. But in the southern hemisphere, the Coriolis force is reversed. It's turning the wind to the left, as you can see here in this schematic. And so similarly, we can draw a pressure gradient force. Realize that since we're in the southern hemisphere, we're going to go clockwise around the low. You may be serenaded by my golden retriever who just found a toy. And the wind is going to, again, go inward, but now clockwise because we're in a different hemisphere. Pressure gradient force doesn't change. Frictional force doesn't change. The Coriolis is the one difference between the northern and the southern hemisphere. And so again, here's a little bit of an example of how things might look if we're in the southern hemisphere. This is pretty much like that graphic earlier that you had of the gradient balance, but also if you just cross things a little bit, you can see the swirl as this works its way inward towards a low. But again, because we're in the southern hemisphere, they're blowing clockwise around the area of low pressure. And so this graphic right here kind of takes home the different things going on at the surface and aloft at the same time. In the left side, again, we're looking on this bottom row of points that are going again from the surface up to about 3 kilometers. So here at the surface, we get our pressure gradient force, we get our surface wind blowing inward and counterclockwise. Again, here we're in the northern hemisphere, it's even in the schematic. And we see the Coriolis deflected to the right, frictional opposing, it's what we just went through. But this same scenario, if you went a few kilometers above the surface and got rid of friction, would simply be our geostrophic balance. Low pressure, spinning inward counterclockwise, go up in the atmosphere. Now you basically have a trough of low pressure and we have our gradient wind balance. High pressure, winds blowing clockwise and outward from a high, here going around a ridge, gradient wind balance. And so the idea of what's happening aloft when we lose friction, it actually is simplified. It's just that we think of things down at the surface because it's where we live. And so a couple more schematics, again here looking at things that may be up around 700 millibars, how things would behave in terms of gradient wind balance here in the northern hemisphere, counterclockwise flow following the contours, this gradient flow around the low. Notice how we get our pressure gradient balanced by Coriolis and then that centrifugal pointed inward. Move things down to the surface. Now we end up still working our way counterclockwise, but because of friction our winds turn inward toward that low pressure. High pressure, still in the northern hemisphere, clockwise flow, gradient wind balance here on the right. Again, simply reverse the pressure gradient as well as the Coriolis. Slightly different terminology and shorthand in this image. But what you have then at the high, at the surface, outward and clockwise. And so we refer to, if I go back a slide, the idea of a low being a cyclonic rotation versus an anticyclonic rotation. And so we'll actually be getting into the next section into cyclones, mid-latitude cyclones, and the idea that these are going to be areas of low pressure, and we'll focus on the structure of a mid-latitude cyclone in the frontal structure. Bayes-Ballott's law, again, this was my one a few slides ago, being the cool kid. Take your body, turn it to where the wind is at your back, or you find the wind at your back, turn 30 degrees, and the low pressure is off to your left in the northern hemisphere. And so this would be if you could manage to float in the air, how it would behave with it directly to your left. Here at the surface, you have to turn about 30 degrees, and then the low would be at your left. Almost there. Vertical, hydrostatic balance. In reality, this is pretty simple. The idea that we have a vertical pressure gradient that we've been talking about since literally day 2 of class. The idea that pressure is that weight of the air above us, and so as you move up in the atmosphere, pressure decreases. We know that. That was the first take it to the bank of the semester. And so what's to keep the air simply from moving from high pressure at the surface towards low pressure at the top of Earth's atmosphere? The answer is gravity. The gravity is going to keep Earth's atmosphere intact. And so we basically have this complete balance between pressure gradient force pointed upward, gravity pointed downward, and this means that we don't have basically our atmosphere go, well, like a vacuum into outer space. That would be pretty bad. So we can be pretty happy for hydrostatic balance. It doesn't mean that hydrostatic balance is always, always, always in effect. Think of some features that we've talked about with clouds and big, tall clouds and how they may be basically able to overcome that gravitational force and build upward. Well, I'm getting at thunderstorms. The idea that you may have things in the vertical not in balance, but these are going to be in pretty isolated patches when you consider the size of a thunderstorm and, well, the world. And so our last slide, we made it. This video is a little bit shorter. The idea of vertical motion and how things behave, and this is going to kind of lead us into the next section. Here again, northern hemisphere around your low, counterclockwise flow in towards the low at the surface. This air piles up and things converge, and it's a lot easier for air to rise upward through the atmosphere than to penetrate into the ground. We get this rising air, and that ends up sometimes creating some clouds. We can sometimes then, when we find convergence at the surface, find divergence aloft. And as you can almost trace some of these arrows, we get kind of a cycle here. Think almost like our cells when we talked about our 3-cell model. And so when we have divergence at the surface, air spreading apart, something's going to fill in this void. We get sinking air from aloft. And so the big takeaways here are rising air is often associated with clouds, showers, rain, snow, thunderstorms. Whereas sinking air is going to be your blue, clear skies, sunny days. And so these are generally what we associate with low and high pressure. And we'll get into this next week. All right, good job getting through these videos. Please continue to work on your assignment. You can work on the book, and we'll get through more of assignment 2, the material in class on Monday. And you can effectively at this point complete your lab that should be ready to be turned in on Thursday. Otherwise, stay healthy, stay well, and we'll talk to you next week.